Hello again. My name is Doug Boling. I'm gonna, excuse me, as we repair a few things. You laugh. She told me if I touch it, it goes. This talk is on video drivers, and when it says video drivers exposed, it basically is, we want to get you into the talk. We're not necessarily going to, it's supposed to have a catchy title to get people into the room. So we're really not going to talk much about video drivers, but it got you in here. Actually, what we're going to do in this talk, before we get into what we're going to do, for those of you who don't know, my name is Doug Boling. I do training for Solomon Expert seminars. I teach both embedded and application programming. I'm a contributing editor to PC Magazine and to Microsoft Internet Developer. Have I got a book? Why? Since you asked, yes, right here. Doug Boling's written a book. ProgrammingWindowsCE.com. I do that so that I can go public, but actually it's Programming Windows CE. It's out of this. It's not in the store right now, but it's at a place called the Torn Page or the Torn Cover or something, which is a bookstore just down the street. I've been told by my dutiful Microsoft Press marketing department, who failed to get books here to the Windows CE Developers Conference. We're going to have a bit of a talk when I next visit Redmond. So we're going to go over introduction to video drivers and talk about Windows CE video drivers. The reason I try to give this talk is because, when I was doing coding and HAL stuff, the one thing that always scared me to death was video drivers. Because those are always the three geeky guys in Silicon Valley that you hire for an infinite amount of money, and they don't work on site. They work back in their cave somewhere, and all of a sudden you have this blazing fast video driver. And I always thought that there was some mysterious thing about writing a video driver. And it works out that at least on Windows CE, it's not. It's a fairly simple and straightforward process. So this talk is basically to rip away all of the mystery about it and just show you how to implement a simple and fairly fast video driver. After we do that, then we're going to look at how we can optimize a video driver, even in the simple mode, even in the simply written mode. We can make video drivers fairly fast. There's a lot of low-hanging fruit that just by a day or two of work, you can literally double the speed of your video driver. First, a few definitions. I see handouts are in the room. Handouts are in the room. So they're going. This is Cynthia. Cynthia is organizing the conference, and she does a great job. I mean, this aside, this has been an incredible conference. So thank you, Cynthia. And she's going to pass them around the middle. A few definitions to start off with. GDI is what we all know as the graphics device interface, graphics driver interface. That's kind of the thing that's been in Windows forever. That's the thing that pushes the bits inside Windows, inside the operating system. DDI, actually, it's not display driver interface. DDI technically stands for device driver interface, but the only time you typically hear it referred to is in display drivers. And unfortunately, the default name for the display driver is DDI.dll. But that's not display driver interface, that's device driver interface. Finally, my friend and yours, the graphics primitive engine. That's what's going to make writing a video device driver relatively trivial for you. And finally, BitBlit, that mysterious thing, which is nothing more. Thank you for the sound effects. It was perfectly timed. BitBlit is nothing more than a mem copy or a mem fill. So when people say, "How's your blit working? Is it fast?" Yeah. You can talk about that, but it's nothing more than a memory copy. But you don't have to tell people who don't know. You can just say, "Yeah, my blit code is really ripping." The Windows CE video driver is based on the NT video driver, but it's much lighter. And the NT driver allows you to do a whole lot of flexibility, and it's pretty powerful. But fortunately, we won't have to write at that level unless you really want to. It works in graphics modes only. There's no text mode. There's no mode 7, mode 3, and mode, what was the other one that you always had to check for in DOS? There's none of that in Windows CE. All we have are just standard graphics modes. You give it an X and a Y so that you have the desktop, and you give it a pixel depth, and you're done. So it's real easy that way. Typically, a video driver in CE supports one mode. It's none of the DOS kind of stuff where you have to support 43 modes. Okay, you just support one mode for your shipping device. Some device drivers are written to support more, but they mainly come from companies that are writing the graphics, they're building the graphics chips, because they don't know what you're going to want. So they'll write a driver that'll have 2 or 3 modes. But Windows CE is only documented to support one video mode per reset. So you're not going to be going into a control panel and changing the resolution of the desktop on the fly in Windows CE without resetting the device. Multiple display drivers are supported. What that means is I can have a screen, which is my standard desktop screen in Windows CE, and I can have another screen displaying completely different information. Now, what Windows CE does not support is spreading the desktop across both screens, like the Mac does in Windows 98 and NT2K. They do that. They let the desktop span across two screens, and you can't do that in Windows CE. But you can, like Pocket PowerPoint on these small devices. On the device, it'll show you your notes, and on the screen, it'll show you your slides, which is better than the PowerPoint Office 2K. Take that, Office team. Windows CE rocks. With all of this ease of implementation comes a few requirements. Windows CE makes a few assumptions, and the driver model makes a few assumptions as to how you're going to lay out your frame buffer. And fundamentally what it means is Windows CE wants a linear frame buffer, and in a second I'm going to talk to you about what a linear frame buffer is. CE supports all sorts of bit formats. Ever since 2.0, Windows CE 2.0, you can have 1-bit propel to up to 32-bit propel. You can have a tiny 240 by 320 display on the palm-sized PC. You can have 1600 by 1200. There's no operating system limit to the resolution of your display in Windows CE. Or the color depth. You can have, like I said, from 1 to 32 bits propel. The 2-bit propel format is unique to Windows CE, and in fact, that's one of the issues when you're developing applications for CE and you start doing 2-bit propel bitmaps. The emulator on CE will actually convert those to 4-bit propel bitmaps, if you have ever noticed. One of the nice things about video drivers in Windows CE is it doesn't take an interrupt. I mean, there's no reason you couldn't implement something underneath the covers if you had to, but there's no requirement in the operating system for it. And in fact, when I'm bringing up a Windows CE system, I typically, after I get done with the HAL, the first driver I bring up is the video driver. Now, I tell management it's because, see, look, I'm done, because here's a desktop. But the real reason is because the video driver doesn't take any interrupts. And interrupts are the hard thing to bring up on the HAL. So if you want to get that, you can bring up the desktop before you actually get any of the interrupts running. That's kind of cool. Power management is supported. You are notified when the system goes into suspend and comes out of suspend. You can do all sorts of things to curtail your power usage on your device. Probably going to turn the backlight off, but there's other things that you may want to do. One of the things that's pretty cool about the Windows CE model is that when you shut down the device, when you suspend, you can ask when it resumes for Windows CE to redraw the entire desktop. And in fact, that's the default mode. What that means is you do not have to maintain the frame buffer during suspend. You can turn off that RAM and shut down that power. And that's great. And when Windows CE resumes, it will redraw the desktop. That's way cool. Now, you can turn that off. There's a registry setting that I can never remember, but you could ask your local Microsoft representative, that will actually disable that so that it doesn't redraw the desktop. And you might want to do that if you've got a frame buffer that uses CMOS static RAM or something like that that's you're going to always maintain anyway. You don't want to see the screen redrawn when you start up. And so it'll actually make your resume performance even faster. Now, this linear frame buffer. When we talk about a linear frame buffer, what we're talking about is a contiguous block of memory. We're not going to have any paging. We're not going to let you put little windows in there and you can page part of the buffer in and part of the buffer out. We're not going to have banks or planes. How many people remember the EGA? Ooh. The EGA, when you programmed it, good old IBM, they said, okay, you've got a pixel. Well, one part of the pixel is going to be over here, and the other part of the pixel is going to be over here, and the third part of the pixel is going to be way over here. That were planes. You had an R plane, a B plane, and a G plane. We don't do that in CE. Well, you can do it if you want to, but CE isn't going to support it natively. The lines must be in a packed pixel format. What that means is pixel 0 is here, then pixel 1 is immediately next to it, and pixel 2 is immediately next to it, packed within the bytes. So if it's a 2-bit propel display, you've got 4 pixels per byte. Okay? If it's a 32-bit per pixel display, obviously, you've got 4 bytes per pixel. You can have gaps at the end of each line. And the distance, the address difference between pixel 0 and 0, 0 and 0, 1, the first pixel of the next line, is called the stride. That is the distance in bytes between the start of one line and the start of the next line. And then you can actually have leftover bytes at the end of each line. But each line must start on a D-word boundary. Here's what I was saying. Planes are not supported, and banking is not supported. Windows CE wants to see a big chunk of RAM. We're not stuck in the in the 1 meg memory model of DOS anymore. So you've got a lot of physical address space to deal with. So you got to use it. You got to have your video buffer sitting out there in RAM, or at least in memory somewhere. Now there are 3 types of video drivers. There's complex and fast. There's slow and simple. And there's the Goldilocks solution, the GPE driver, which is just right. Okay? It's fairly easy to write, but it provides the ability for you to accelerate. And we're going to spend some time at the end of this talk accelerating a GPE driver. To talk about how these drivers relate to each other, let's look at the video model that Windows CE has. You start up in the operating system with GDI, and GDI is part of GUI. It's the thing that draws the lines and pushes the pixels as far as what the application sees. And what that does is the GDI then sends commands down to the display driver to implement these lines and these bitmaps and these things like that. Now that interface is called the DDI interface. That is the interface between the display driver, or the device driver, which is the display driver, and the operating system. That is the interface. Below that, my friend and yours, the graphics primitive engine. That is a library provided by Microsoft. You don't get the source code to it, you just get a lib. You can statically link to that when you build a driver. And that translates that fairly complex DDI interface that I'm going to go through in just a second down to a relatively few number of method calls that you have to implement. Ooh, methods. Yes, that means, for ladies and gentlemen, that this is the one driver in Windows CE that is C++ from the ground up. Yuck, but it's there. We live with it. I mean, I'm a guy that thinks a C language is the thing for weak minds who can't remember machine code. So, C++ is even worse. So you've got the GPE driver, and that's the code you would write that interfaces with the graphics primitive engine. Below that, if you need it, you would have a dirty rec driver. That would translate the image that the GPE driver would write, and that would translate it to some non-standard video hardware. So if you're going to do a DDI model driver, what you do is you do the whole kit and caboodle. You start with the DDI interface and you slam to video hardware. Windows CE lets you do just about anything, because you'll notice that in a few minutes that the DDI interface is very high level. So that whole talk that I just gave you about linear frame buffer, if you don't want to, you can forget about it. But then you have to write this whole puppy. Or you have to do a dirty rec driver, which is slower. Now here's a bit easier DDI model, and the reason it's easier is because there's a sample provided for this in the platform builder. And I'll tell you in just a second where that is, but there's a sample in there that provides a DDI interface, and then there's a linear, but that driver assumes a linear frame buffer, okay? And that kind of subsumes the dirty rec issue, so there's really no dirty rec on that. Now, this is the driver almost everybody writes. You write the driver code in the middle. You write the GPE class library. You link statically to the graphics primitive engine. You assume a linear frame buffer, and you're done. That's what we want to do, because that's the easy path to good stuff. If you don't have compatible linear frame buffer in your hardware, but you want to write a quick and dirty driver, you can write the dirty rec driver. And literally what that means is that the system is going to render the image in system RAM somewhere. And then it's going to notify you when there's something dirty on the display, that is something in RAM that is not on your display, and then you copy that rectangle to your display. Okay, so you can see because of this extra copying, you're going to have a performance issue. Now, here are the DDI functions. Let's go over them in detail. Drive any bit. I'm not going to do that to you. This is the first slide of it. This is the second slide. Yeah, well, I'm not going to do that. So those are the two. The reason I put these up here is to show you what you have to do if you want to do it. It's here fundamentally for reference. But you could spend a day or a week on a class describing how to properly implement this. Because as you can see, it's a really high-level interface. You've got, move, pointer, drive, paint. I mean, literally, you have to render everything. Drive, realize color, drive, set palette. Start dock, start page. Those are actually things that you implement if you're doing a printer driver. And oh, by the way, printer drivers are very closely related to display drivers in Windows CE. Is there any provision for rotation? Not in the spec. No. Depends on if your hardware can rotate a linear frame buffer. And there are chips that will do that. So you should find, and I'm not going to push specific graphics chips. The question was, is there any support for hardware rotate, or any support for rotate in this model? And there is no support for rotate in this model. There's no reason you can't do it. You don't have to be a direct driver. There are chips out there that will do rotation in hardware. And there are accelerated chips that will actually make the direct fairly fast because they can actually suck it out of RAM pretty quickly. There is something up here, and I don't know if it's in here. There's a drive escape call that has been added, and it's getting new relevance in 2.12 because they're going to actually let you go in and do escape codes, and that's kind of going to be the new backdoor. That's basically the ioctl to the display driver. Now, if you're going to implement all that functions, you've actually got some helper functions that you can call back into GDI to actually help you with some things. And so these are some services that GDI provides back to you, the driver. But you don't need to even know about this unless you're going to do a DDI driver yourself. The sample DDI driver is in CEPC drivers display S3 Trio 64. Okay? Now, that assumes a linear frame buffer, but the interesting thing about this, as I like to say, the documentation for Windows CE is in the source code. Okay? It's in the examples. And the interesting thing about this one is, obviously, the person that wrote this driver inside Microsoft probably could see how GPE, he could probably look over, or he or she could look over and see the source code for the graphics primitive engine. So the way they drew a blit may be the way he drew a blit. So you can kind of get some hints on how to do blits and things in your own code in looking at this driver. There's also the emulation library we'll talk about later, and you get the source for that, for how to accelerate things. So that's enough about DDI. I'm really not going to talk about it much more. What I want to talk about is the GPE model. And the GPE model is way cool because it allows, like I said, acceleration, fills blits and lines and things like that, but it's a really simple model. It was introduced in 2.0, which was actually the first time you really got to do a display driver at all, for all practical purposes. And what you'll find is that most graphics chip manufacturers out there are providing GPE drivers as their example drivers. Now again, here's the diagram of what you're going to have to do. You're going to have to do that middle part, the driver code. Everything else is going to be done for you, which is really nice. Now like I said, this is C++, so you're going to implement a GPE class. You're going to derive it from, you're going to name it something different, but you're going to derive it from the GPE class that's provided in this, when you link to the GPE lib. You're going to implement the necessary methods. You're going to export one function, drive enable driver from your DLL. Because remember, it's Windows CE, so your driver is nothing more than a DLL. Now, what I see almost everybody doing is copying the closest driver they can find and hacking it out, because it's just the easiest way to do this. You could build it from the ground up if you wanted to. Now let's go over the methods. And the reason I'm going to go over the methods one by one is because, frankly, there aren't too many of them. Okay? So in the constructor, you're going to actually have to, here are two functions here. The constructor, obviously, you're going to initialize the video controller. And this basically means turning it on, getting the frame rate set for the card or the whatever monitor you're using. You're going to implement that. And that's fairly straightforward. That's whatever you need to do for your graphics chip. Then there's number of modes. And there's an interesting thing about number of modes. Because what happens when GDI wakes up, and GUI wakes up, and it calls down and loads your driver, it's going to initialize your class, and it's going to call down in there, and then it's going to call num modes, and you're going to return 1. Okay? And then after that, it's going to call set mode. Okay, yeah, I kind of led in a little early. It's going to call set mode, and that's where you're going to initialize this one mode. Okay? And that's actually the prototype for the function. It's really trivial. Then after it does that, it calls the next function called getModeInfo. Now, getModeInfo is cool because basically what it does is after it set the mode, it's going to say, okay, how big are you? What's the X and Y, what's the size of the desktop of your screen, and what's your color depth? Now, the cool thing about this is, once I was asked to hack out a driver, and they wanted a driver that would support 640 by 480, 640 by 240, and 240 by 320. Those are convenient resolutions for Windows CE, right? And they wanted this all on one hardware platform, and I did it in an evening. Not because I was really smart, because all I had to do was change the mode information returned by the driver. And I would look in the registries. Oh, this time he wants to look like a palm-sized PC. So the screen and the display buffer was 640 by 480 because that was the size of the native hardware. But I only reported back 240 by 320. And so it built a nice little desktop inside of 240 by 320, and it was done. So you can actually, especially for testing, if you're doing applications and things like that and you want to play around with different screen sizes, all you have to do is change what you return back in get mode info. Now, here comes the power. This is the key. Now, again, this first stuff is, let's go back just really quick. You had to initialize the display, really trivial. Number of modes, you hard code that to 1. Set mode, you initialize the mode. All of those things are graphics chip dependent. There's nothing much we can do about that to simplify it. But now you have some fun. Because here's the blit call, the ominous blit call. And there's actually two functions, methods. There's two methods in this class. There's blit prepare and blit complete. Now what they do is before every blit call, the GPE driver is going to call down your method and say, here's the blit I'm about to do. And what your job is as the driver, is to return a function pointer to the function that's going to implement the blit. Well, that sounds pretty ominous. Fortunately, all you have to do is, if you want to, is return the default emulation function provided by the GPE driver. You're done. It's about 5 lines of code. I'll show it to you in just a minute. So that's all you really have to do is if you want to get something up and running really quickly, is you just return emulated text blit, emulated blit, and you're done. After it, what it does is it calls blit prepare, you return a function, it calls that function. After that function returns, it immediately calls blit complete. And the reason the GDI calls blit complete, the graphics primitive engine, GPE, calls blit complete is it wants to have a synchronous display. It doesn't want you, if you've got some hardware acceleration, to return from blit complete until the hardware acceleration is completed as well. So it wants the display updated before it returns from blit complete. Now the nice thing about this is, because it's done in real time, it's done for every blit, you can decide at that moment, are you going to accelerate this specific blit? And what that means is you can cherry pick. This is an easy thing. I'm going to only accelerate full screen fills starting on even numbers of lines of, blah, 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 of solid colors. Well, that's a memory fill. Anybody can do that. And you can do that really easily. So, and frankly, fills are one of the first things you want to accelerate in Windows. So you can actually in a day, you can upgrade the blit code to do just the one thing that you want to do today, and it'll make it just enough faster. And tomorrow you can do something else. So you can incrementally include. So that's the blit function. The line function functionally is the same thing, the line method is functionally the same thing, but for some reason they implemented it in one function instead of 2. And the second parameter, GPE phase, line is called twice. It's called with the GPE phase being prepare, and you return a function to the line acceleration. Then it's called again with line complete. So it actually calls this one function twice, as opposed to the way the blit did it. I don't know why they did it this way, but hey, it works. Now, just like the blit, it asks you for the function to implement this. And what's simple is they provide you an emulated line function. So if you don't want to accelerate lines, you don't have to. So the line method is, like I said, this is a repeat of what I just said. It just basically says that you can provide your own, or you can just return the emulated function. Now, the pointer functions in Windows CE for touch panel devices can actually be stubbed out. And this is great. If you think about it, what's the one pointer that we all need in Windows? You cannot survive without. The hourglass. Forget the arrow. We need the hourglass. Because on touchscreen devices, we don't have the arrow. Right? And on touchscreen devices, you actually get rid of the pointer component in the cursor component, most of the cursor component in GUI. And so what happens is when you get the fake cursor componentized into GUI, it emulates the hourglass with a little tiny window, which means it doesn't force the display driver to have to implement all of the pointer functionality just for the hourglass. And so that's really nice. So you only have to do these two functions if you've got a mouse-based display, or mouse-based pointer system. Set palette, also very simple. You set your palette. That's a hardware implementation detail. They're going to give you a list of palette colors and entries, and you've got to slam them in there. Now, I've never seen anybody implement NV blank, and actually what you do is you can check to see if you're in the blanking interval. Those of you who were back in the DOS days remember that the CGA said you could only write to the display buffer during the blanking interval. I've never seen Windows CE implemented on a CGA, but perhaps somebody does. I mean, I literally have never seen anything on vblank except stub that out, but maybe there are some examples, some places where you need it. Okay, so that's the entire class. That was all you had. Okay, we had to initialize the mode, right? We had the blit functions, we had the line functions, but those you can emulate out, and we had the pointer functions that we're going to ignore because we're going to use touchscreen. We're done. Okay, these are fairly simple. You've got excuse me, this is the last method. You've got Alex surface, and fundamentally all this is asking for a memory buffer. It calls Alex surface to allocate the display, and then it calls Alex surface again for some bitmap caching, things like that. And it will suggest I want to be on the display memory or I don't. And you might want to try to, why would you want to have off-screen, why would you want to give it off-screen video memory? Because if it's going to cache some things, video memory to video memory with hardware acceleration is much faster. So there are some reasons to actually say, okay, if you want more memory, I'm going to give you the off-screen video buffer. But it will call it at least once Alex surface to allocate the display itself. Now, the other classes are the surface class, which is basically just the class that describes the thing that was in Alex surface, the method before. And that's really simple. And then the node 2D class is nothing more than a trivial class that you return when it asks for get display info, or I forget, get mode info, I think is the method, and which is the resolution, the depth, and the stride. So that's it. Okay? Why did I drag you here? Well, we'll talk in just a few minutes about acceleration, and we'll do some fun things there. But before we go into acceleration, let's look at the dirty rect driver. The reason the dirty rect driver exists, I mean, fundamentally was backward compatibility with 1.0 devices. This used to be the only display driver you could have if you were going to have a display driver, because in the 1.0 days, GPE slammed straight to the display, and that display had to be 2 bits per pel, linear frame buffer. That was it. And if you had anything different, you had to write and implement a dirty rect driver. And they've kept it since the 1.0 days for backward compatibility, but it's also a great way to hack something together in an evening. I mean, if you need something working and you don't know how to get a linear frame buffer out of your hardware, but you know how to get it set up, then you can implement a dirty rect driver, and all it becomes is just copying the rectangle over. Okay, so you can implement it fairly quickly, even quicker than a GPE driver. And this just represents in our hierarchy what you're trying to do now. Now, you don't really implement a dirty rect driver. You're actually implementing a GPE driver, but it so happens that the source code in platform CEPC drivers display VGA 8-bit per pel is a GPE driver that has some extra calls that you can make that they export for you to implement just the dirty rect functions. So there's source code here. It's a GPE class driver, but all of the GPE stuff you can ignore, and then there are some extra functions that you just fill in and implement the dirty rectangle functions. Now, one of the irritating things about many Microsoft examples, and this one included, is this one tries to support 12 or 14 different display drivers. Therefore, as an example, it's unduly complex. So what you have to think about when you're looking at this example is strip away all the if-defs and strip away all of the support for Trident and Appian and ATI and all the other drivers, display cards that are in there, and just strip it out. And when you get down to the brass tacks, it's a fairly simple driver to implement. Okay, all you have to do is init the display driver, tell the system where the buffer is going to be in system RAM, and then when you're called, you just copy the stuff over. And that's all really you have to do. You do get a few extra functions for contrast and power notification, and obviously the palette and power functions, pointer functions, excuse me. Here they are. They're fairly straightforward. They're just here for reference to show you how simple you can do it. Let's get to the fun part. Acceleration. As I said, GPE is great because the GPE class driver is great because it allows you to cherry pick the acceleration you wish to do. And so we're going to spend a little bit of time on this. Now, the default thing for many of the drivers you're going to get from your graphics chip manufacturers, especially the ones that are a little bit older, that they weren't very confident in the display model, basically all of the blit functions just return emulated blit as the function, and so they are not accelerated. Now, emulated blit is implemented in the GPE class. I mean, it's implemented back up in the GPE library. And the problem with emulated blit and emulated line are that they don't know what your display color depth is. Okay? So they have to go through on every blit and say, oh, is this an 8-bit propel display? No. Is this a 16-bit propel? No. Is this a 24-bit propel? Okay, then I'll do this, this, and this. So it's rather slow. So the first thing we can do without any work at all, in fact, last night I was playing around and I had to cripple a video driver so that I could make it really slow. And so all I did is I put in 4 lines of code that you'll see in just a minute that returns emulated blit. And then I had to upgrade it to use the emulation library. The emulation library are a set of functions that Microsoft provides on the public side of the Platform Builder tree, which are resolution-specific blit functions. Okay? All you have to do is cherry pick and use those where you can, and you'll get a 2x display driver performance improvement. 2x. Okay, just by using a different software driver. Okay, we're not even talking hardware yet. After you've done those, then you can go back and you can rewrite for very specific things. Maybe you have hardware acceleration, or maybe you can write in assembler language a fill that is faster than their emulated fill. Or you can do other things. There are a lot of tricks you can play with display drivers. But that's left to you to write that really tight blit code that those people that live back in the caves can do. So this selective acceleration strategy is really, really great. And let's look at it for just a second. I'm going to give you an example here. I'm going to switch just for a second to this is my laptop. Now, oops, I'm up and running. I'm going to sit here. I'm in the release directory, and I have a number of display drivers. Now, what I've got here is DDI fast and DDI slow and DDI emulation. Now, the system that's over here has got in ROM everything. I've flashed everything but the display driver, which, by the way, if none of you have done it, know how to do this, you build an entire ROM using make image. Then you go into CE.bib and comment out the one file you're trying to develop. And then you ROM image CE.bib. And that gives you an image with everything but the one file that you are trying to develop. You flash that for however long it takes. But then from then on, when you hit reset, the system's going to boot up very quickly because it's in ROM, right? Or in flash, excuse me. But when it needs that one driver, it's going to suck it down from the release directory using CESH. So even if you've got the CESH link as serial, it doesn't matter because you're only now bringing down one driver per boot. And so it's really cool that way. So I'm going to go copy DDI slow.dll DDI.dll. And I'm going to go CESH. And I'm going to reset my device. Oh. I'm going to reset my device. Okay. And I'm up, just to make sure. Yes, I'm there. As you can see in the background, you can see all the messages going up. And I'm up, and if I do a GI again, you'll see up there DDI is mod 03. So I'm sitting there, and I've got my DDI driver, which is the display driver, loaded and running. Now, I've got a program I call fill test. And there are, starting with 2.12 or 2.11, there are some performance calls that you can make, some profiling calls you can make using the display driver, which allow you to precisely meter how fast your blits are going. Now, I didn't implement that for this discussion because basically a lot of people are not on 2.11 or 2.12. They're back in the old days. And all I did here was just do a fill test. I created a window with a standard application. I created an application. And all it does is create a window, full-size window, and fill it with black and white. Okay? So if I go start fill test, it's going to run, and it's running over here. You can't really see it. Or I could switch over there and you could see it for just a second. But by the time I get over here, it's going to be done. And it's already done. See, I told you couldn't make it fast. And what we see here, and what it does is it does get timer ticks at the beginning, get tick count at the beginning and get tick count at the end. And the elapsed time, for those of you who can't read it, is 6.678 seconds. Okay? This is using, now let's look at that driver. Let's look at the source code for that driver. We're not in classes. We're done in Windows CE 2.12, Platform, Clio, drivers, display, set 1354. And then if we'll look at blit, slowblit.cpp, this is just what you want to name something for your manager. This GPF'd in my last talk, so we'll hope this Dev Studio is going to work this time. Now, we talked about blit prepare and blit complete, and I said it was pretty simple code. Well, look what I've got in here. I've got all this extra stuff. What is it, though? It's nothing more than debug messages. I can take that stuff out. You see that all of the debug message stuff is just in there to report on, what's going on, and I don't really have to have that in there. The whole code for this, the whole functional code for this example is right here. Params, pointer to blit function is equal to emulated blit, and that's it. SOK. And that's the entire blit function for blit prepare. Now, blit complete's a little more complex. Oops, that's not what I wanted to do. Yes. There's blit complete. So you can see I've got a really complex blit function, but it works, right? I didn't have to worry about it at all. I've got a driver that is up and running, and I'm happy with it. Because now I can show it, and you know what? The app development people can start to work, and I've got a desktop, so the manager's happy because they can show it to their manager, see, something's running. And so everything is good, but it's obviously not very fast. So let's go back. The quick fix is the emulation library, and horizontal and solid lines. And then later we'll look at some other optimizations. Now, I want to go through these first because this is important. Microsoft has a white paper on this, and they tell you these are the accelerations you should work on first because these are the things most called. Okay? So you want to do these kinds of accelerations first. First one is the easy one, solid color fill. Now, why is that important? Because when every window is created, what's the first thing Windows does? Fills it with a brush. And then it goes on drawing what's in that window. But first it fills. And since we're Windows CE, most of our windows are full screen. So it's a big fill. So you really need to optimize solid color fill. And fortunately, it's trivial. It's nothing more than a write constant to memory. Really trivial. Now, after you get that one accelerated, then you want to do source copy, which is nothing more than memory copy. That says the system in its blit is going to take, say, move this rectangle from this location to this rotation, or copy it, excuse me. Copy this rectangle to this location. And so that's the second most important thing you want to accelerate. After that, cursor display is important, but only if you have a touch, a mouse-based system. And then solid line. Now, solid line is drawn. Why solid line? Well, when there's a lot of little details drawn around on your Windows display, right? But what's great about this is solid lines. I mean, lines can be difficult because in this case you actually have to. It requires sub-pixel precision, which means they really want you to do very good diagonal lines. And so you know what I say in response? I'm not going to do them. Okay, I'm going to do the horizontal and vertical ones. Why? Because that's what's almost always drawn. When you draw a window, Windows CE doesn't support non-rectangular regions. So all windows are rectangular. So they're going to be drawing horizontal and vertical lines to draw those windows most often. So you just draw the horizontal, you just accelerate the horizontal and vertical lines. It's really simple to do. Finally, mask source copy. Now, when I said blit was nothing more than a memory copy, that's an understatement because blit, you can actually get the source, and it with the destination. Get the source, or it with the destination. Get the source, and it with the mask, or it with the destination, and ad nauseum, because it's a logical operation. So you can get very complex blits. But at one point, they want you to do a mask source copy blit, and that's the next thing to accelerate. Now, if you want to do blit acceleration, during blit prepare, you just check to see what kind of blit it is. Now, a solid color blit has a ROMP code. Now, a ROMP code is basically the 32-bit code that describes what kind of operation is going to happen. And those are actually binary operations, each of those bit fields, but you generally don't mess with them. You just look at some constants that are there. I mean, some equates that you get out of the include file. A ROMP code of 0 or all foxes, or a ROMP code of fox 0 with a solid color, those are solid color fills. And so if you just do an if around those things, and then you accelerate that, because those are really easy to accelerate. And finally, source copy, which is a ROMP code of CCCC. So when you discover these things, all you do is set that pointer, instead of pointing at C. The first thing you do in blit prepare is always set the function pointer to emulated blit. Then you start cherry picking. After you've done that, you say, if it's this, and this, and this, oh, I'm going to use my fast one. Else, it just uses the default. Okay? So we'll see how that works. Now, Microsoft gives you a bunch of emulated blit functions that are resolution specific and therefore much faster than the emulated blit function provided by the GPE Lib. Emulated text blit, source copy, fill, blit acceleration. Now you see the x-axis. What that means is they have 2, 8, and 16-bit functions, versions of each of these functions. So it would be emulated text blit 02, 08, or 16. So there's 3 different emulated text blit functions. Now there are a few more functions if you're doing, excuse me, what's going on here? Okay, ignore the first slide was, okay, this is a repeat of the first slide, I apologize. These 3 functions are only provided for 2 and 16. And the reason they aren't provided for 8 is because if you look at they involve color. And an 8-bit propelled display uses a palette, and the blit library doesn't know what your palette looks like, so it really can't accurately do these color accelerations. So they don't do it on an 8-bit propelled display. Doesn't mean you couldn't write it yourself because you have the knowledge of what your palette looks like. But they have 2 and 16-bit propels already for you. Now, this is just to intimidate you. When called blit prepare, this is the structure it provides you with. Now, I'm not going to go through this in detail, but what you see here is you get all of the information you could ever want to know, and probably a lot more, on to decide if you want to accelerate this. Here is some code right here that accelerates to use the emulated functions. In fact, this accelerates solid color fills. At the top, look, I assume I'm going to use the emulated function. After I do that, I start cherry picking. Well, am I at my proper resolution? Yes, I am. Oh, look, the ROMP code is for filling black, filling white, or it's a pattern copy with a solid color. And if it's any of these 3, I provide my own fill functions. Else, I just continue on. And continue on means I use the default emulated blit function. So the nice thing is I can cherry pick like this. Now let's go over here. And let's look at imoblit. Imoblit is just what I showed you. Again, this is the start of it, which is nothing more than debug messages. Here's the catch-all right here. Always assume you're not going to do anything. And then go down here and say, oh, look, is it going to be, make sure it's for the display and that you're going to do exactly what you want. I mean, this is being used for the display, not the printer. And then I start checking ROMP codes. Right here, ROMP4. Is it black, is it white, is it a pattern copy, or is it a source copy? And the source copy actually has a different blit. As you can see here, this is blitfill 08, and the func name is nothing more than a macro that's right up. Where's func name? It's implemented. I may have implemented in the include file. It's nothing more than a macro that composes the proper name for that function and typecasts it correctly. But you can see right there actually, the top one there is a func name blitfill08. Then down here is going to be a blit source copy 08 to 08. And then down here is a blit text 08. So I'm doing text acceleration, I'm doing source copy acceleration, and above the screen I was doing solid color fill acceleration. Now, this looks like a lot, and you can see I'm trying to cherry pick all of the fancy things I can get without doing any code myself, because all of these point to emulated functions. I'm not doing anything I'm not writing any blit function so far. And then down here, blit complete, which obviously does nothing. So now let's look at that library real quick. DDI emul.dll into DDI.dll, CESH, boot. Let's see, did I boot? I don't think I did. What's happening over here is the system is shutting down for power reasons. Don't need to have the battery driver in there. Are you up? Yes, you are. Okay, so I'm up and running. So now I've got a different DDI, and unfortunately what I should have done is provided some kind of text out message so that you would know I'm not faking it. But you don't, so. So let's do our fill test again. And this time, I'm going to actually show you what's going to happen. And that's all I'm doing here is doing fill test. It's just filling in. Oh, wow, I'm done. My goodness. 3.304. I just doubled the speed of my display by taking about an afternoon's work. Okay, use the emulation libraries. They are, I don't know, I hear conversations, I go on the floor, and I know some of the hardware behind some of the models up there, and I go, I hear, man, that CPU is really slow, or this is that, or this is blah. Typically, when people see a box up there and they see that it looks slow, it's not the CPU. Because all the CPUs have roughly the same horsepower if you count in the memory bandwidth of the bus and that kind of stuff. The difference in a lot of the things is how well the display driver was written or if the display driver has hardware acceleration. Okay? And that makes an amazing difference. Let me show you. I'm going to go back to the slow one. What's that? That, just for emphasis? The display driver in GPE is not optimized. I was prompted by my Microsoft watchers. And fundamentally, they're not. I'm just teasing. They've actually got a little button here, and it shocks me every time I see something wrong. It worries me sometimes. I have to be very nice to them. The display driver isn't optimized, and you gotta optimize it because, and you know what? You saw what I did. It was just trivial code. I didn't write one blit. I took that code and I copied it from an example in CEPC, one of the display drivers from CEPC. I just took that code, slammed it in there. And the only reason I got a compile error is because they were using different variable names. And once I did a search and replace, it worked, and I doubled the speed of my driver. And it makes an amazing difference in Windows CE if you've got a good display driver. Am I up? Okay, this is a classic test. This is a classic test right here. We'll switch to 8. Oh, did we lock? We did lock. We'll try this again. Am I up? Good, 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 good. I'm happy. Now, the classic test. Now, there's two classic tests that I do. I do one to do CPU speed, and that's basically display all files in the Windows directory, put it on text on detail mode, and then sort by file type and measure the time on that. And that will tell you the CPU's core speed, because that's a sorting algorithm, and it's not dependent on CPUs. I mean, it's not dependent on anything else. So that's a great way to compare CPUs among these platforms. But if you want to compare video drivers, you do this. You get this box up, and you start up a command line. And you can't see it here, so I'll bring it back over here. Now, normally, you don't have CESH attached in the retail store, so you would just go to File, Run, S command. But I'm going to launch it from there. And over here, you will see a command prompt. And actually, the zoom isn't very good. It's at the very top of the display. So what I always do is I do help, and that's just drawing the text, and that looks okay, right? Then try something like this. Make it scroll. Now let me tell you, the CPU in that is very fast. It actually is a very fast CPU, but it's painfully slow to scroll. And that's because this is the slow driver that I was just showing you about. And what kills me is there are companies out there that shipped that driver. Control-C, okay. So you saw how painful that was. So let's go back here, and let's do a Control-C. And let's go, just by the way, you see this. Why is that so fast? It's not because a Pentium is so fast. It's because every video chip on a PC is accelerated. Okay, so now let's copy. Let's just do the emulator driver. I'm superstitious, and I feel as long as I do a GI and do get information that the thing's not going to lock up. Okay, so now we have started a command line. Switch back over here to my classic scroll test. Now, you really can't tell much difference in the text split. But you can see twice the performance in scrolling. Now, this isn't great, but it's a lot better than it was. Okay? Just by a software thing. They didn't have to change their hardware. By the way, there are companies that have discovered this after they shipped, and there are certain companies out there that have updated video drivers that you can download off the web. So ask your OEM for updated video drivers, because you can build, even if they didn't have hardware acceleration, they now have this thing, right? Now, companies have done things beyond just trivial hardware acceleration in terms of proprietary stuff. So I'll show you an even wackier one. Okay, CESH. I'm not going to switch back, but I'll just trust me that all I'm doing is the exact same thing I just did. So now we'll start a command line. Okay, this driver is even faster. Okay, and they use some proprietary things that they do to make it faster. No hardware acceleration yet. Okay, so you can spend a little bit of time, but let me tell you, if your company is going to put a display in front of a customer, you ought to spend a little bit of extra time making sure your video driver's fast. So that was blit acceleration. Now, again, what I did there, the first one was no acceleration. The second was just to use the emulation library. The third was to use some proprietary software techniques to make it really fast. There is no emulation library for line functions. But fundamentally, guys and gals, or ladies and men and women, it is not rocket science. A line, especially horizontal and vertical, think about a horizontal line. You know, a horizontal solid line is a single pixel right, okay? Or maybe multiple pixels, but it's very trivial to implement. So implement, and I'm sorry, so it's vertical lines are a little more complex. It's right, add stride, right, add stride, right. Okay, so it's a little more, you've got actually, you're incrementing by more than one. But it's really simple to do. So you should accelerate just with your own hand-written acceleration functions, the line parameters. Now, how do you figure this stuff out? Well, here's the line parameter structure, which I don't want to go into in much detail. I've left you some documentation in terms of the slides. Well, we actually, yeah, you do now have slides. To describe what some of these feels. For example, the direction describes the direction in terms of its octant, and then you've got the CPELs as the length of the line, things like that. But fundamentally, all you're interested in is knowing if it's a horizontal line or a vertical line, and you do that by checking either dn or dm equal to 0. Now, simple line acceleration, you just slam it yourself, and I don't have any examples of that because it's not as sexy as showing how fast the blit makes a difference. So, pick the low-hanging fruit. Spend a day, implement the emulation libraries. Implement calling the emulation libraries. You'll get amazing performance improvement. And then you can go tell the boss that you doubled the clock speed of the CPU. He won't know the difference. Know your hardware because, for example, let me give you an example. I know of a client that had a video hardware chip that I thought, well, I'll make it faster. I'll write 32 bits at a time to the chip. It was slower. Because the chip only had a 16-bit write buffer, it was actually slower to write a D word to it than it was a word at a time. And what it was doing was it was stalling the processor while the write buffer emptied and they could grab the other 16 bits. So instead, write 16 bits, go grab another 16 bits or do some other work and then come back. So know the speed of your hardware, even if it doesn't have hardware acceleration. Know the speed of that bus and know the speed of how that processor, how that graphics chip can accept your writes. Watch out for the compiler. I have seen compiler bugs pop up. And they pop up because they were using some of the standard memcopy and memthing and memset functions in the C library functions, and it was causing bugs in the driver. So I've seen that. Implement this stuff in small little chunks and get it out to your users. Get it out to your beta testers. Because let me tell you, you cannot test your driver like a user can. Okay, they can find ways of dragging some silly window or some divider bar or something in a list view control to give you what I call pixel droppings. You know, you slide it over and all of a sudden something's not drawn anymore. And then what they do is that, they come back to you and they tell you this is how they did it, and then you can go figure out what's wrong. But you're not going to be able to test like a user can. So implement it in steps and then test it. And users hate this. I mean, I've had management say, I'm ripping out your driver because it's not perfect. Okay, I see a pixel there. I mean, they'll if the audio driver is a little bad and has a little static, they may accept that. They do not accept problems in a video driver at all. GPE drivers are easy to implement, and so that's really kind of the best way. If you have problems, you can either go to the DDI, the full implementation, or to the dirty rect. If the GPE model doesn't fit your hardware. Look at performance because you can almost always improve it with just a little bit of thought. Shameless plug, buy the book. Actually, it does not cover video drivers because it's an application development book. So I won't tell you to buy the video drivers. And shameless plug number 2, I do seminars. Questions? Yes?
You mentioned that the GPE driver initialization happens in the constructor.
Some of it does. It's your option, yes.
How do you indicate failure of the driver?
How do you implement? I'm trying to think in the constructor. Blah, 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 blah. Fundamentally, if your driver does not come up, GUI is going to die. So the failure mode is the system not coming up. There is no failure tolerance in GUI for the driver. That's okay. Just yell it out and I'll repeat it. Okay. Number 1. Well, yeah, stand at the microphone. It looks good. Besides, that way you don't get too close to me.
If I understand correctly, in Windows...
Oh, it is running now.
Hello? Excuse me. If I understand correctly, in Windows NT, it was possible to create a engine-managed surface, and all the rendering algorithms were in GDI. So DDI driver could simply punt back to GDI and have the GDI do all the work. So do I understand correctly that all the rendering algorithms have moved in Windows CE to GPE, and DDI driver cannot do this anymore?
Yes, the DDI driver model in CE does not have the option of telling GDI to go back and ask for a simpler call. You're on your own.
Thanks. Question number 2. I've noticed that in the structures that the driver gets for bitblit and lines, there's only a clipping rectangle. How is complex clipping handled? Is it broken down to simple requests?
I'll be honest with you, I don't write DDI drivers. So
no, not the DDI, the GPE.
The clipping stuff?
Yeah, the complex clipping, which is more complex than the rectangle.
Yeah, I mean, you have to do it, you have to implement it that way, and I don't...
in the structure that you've shown,
yes.
the member is the clipping rectangle.
Yes.
What if the operation is clipped to something that is more complex?
I don't know that it is ever, but I cannot answer that question for sure. I think Mark can. There's only one mic, but lean close, big guy.
Basically, it'll come down as multiple
It's broken down?
You'll come down as multiple blit per pairs with the different clipping regions. And that's why you'll actually only get a single blit complete at the end of a series of blit compares.
Oh, I see. So you can get multiple prepares, you accumulate these things, and then...
And the point of a blit complete is actually in some hardware you might have to unset a clipping region that you've set for the most recent blit. So you get a series of blits, and then at the end of a particular graphics operations, you'll get a blit complete, which lets you clear it for any other operation that comes down.
Thank you. And it's the last one now. Can you talk a bit more about how the text blit is handled? And there's a text blit method. And why does Windows CE only allow either a true type or the raster font, and not both?
Why does it only support? Basically, it's a component. We just tried to figure out what's necessary for our products. I believe you could actually include both fonts systems.
Well, that's what
I don't think I've ever seen that done, but...
yeah, that's what not I saw in the manual. It said you can only have one. But
that may be true. So it's just we hadn't had enough people asking for both at once.
So is it possible to accelerate text blit?
Yeah, that's the AAF0, is the text ROP. and that'll come down as a masked blit, and the mask is actually the character.
Okay. The glyph.
Yeah, and again, that's already implemented in the emulated blit library, so you can look at that and see how that's implemented.
Thank you.
It's a pretty decent implementation. The main thing, if you really wanted to optimize any of the emulated blits, it would be to hand code some of them in assembler for your particular hardware, which we obviously don't want to do because we want to support lots of processors.
Thank you.
So first of all, I want to start with a simple question. Is the palette owned by the video driver or by GDI? So if I were to call ENG create palette, is that ultimately being passed down to the video driver?
Yes. Yeah. Yes.
So my question is actually relating to printer drivers, and you alluded to the fact that they're closely related. In fact, the printer driver is heavily dependent on the video driver because currently CE does not allow the video or the printer driver to do its own rendering. GDI actually calls into the video driver to render the image for the printer driver. So conceivably, and actually I've run into this problem, that a printer driver wants to get, say, 300 DPI 24-bit data, but a video driver written for a video screen for a typical CE device is going to be something like 640 by 200, 256 colors or something. So conceivably, the printer driver could be limited by the video driver not supporting 24-bit because it figures I'll never need 24-bit because I only support 256 colors.
One of the things I didn't mention in my acceleration thing is the first thing I checked was the pixel depth. And if the pixel depth wasn't what I was expecting, I passed emulated blit back so that it would render it in the default thing that you're asking for. And so that's why that check is for. That's what that check exists for.
So is it conceivable, though, that somebody would write a video driver that wouldn't perform that check?
If they made a boo-boo.
Okay.
Those of you writing video drivers, you should definitely test with printing since it does go through the main display driver for rendering.
Yeah, another issue also is that a video driver typically expects to be able to put all of its memory for the entire page in memory at the same time, whereas a printer driver obviously at 300 DPI 24-bit depth can only implement it in bands because of the memory constraints on the system. So the video driver should also be ready to handle banded calls by GDI instead of just basically rendering for the full screen.
Yes.
Thanks.
Yes. Next question.
Are the emulated resolution-specific libraries, are they in 2.11?
Yes. And the source code is there.
Is there a 4-bit per pixel version?
No. Unless it's inside Microsoft. Oh, I'm sorry. Yeah, the question was, is there a 4-bit per pixel emulated library? And where are they? They are in, well, I don't know of any 4-bit per pixel libraries. And as far as the emulated libraries, the source code is actually on the public side of the tree. Public comment oak lib, oak drivers, IML. Thank you. Next question. Yeah, I think that's a real pain. Excuse me. In 2.12, there is a contrast control escape going to be in the display driver. In fact, there is a contrast control thing that comes down through GPE. The problem with that is that before you really couldn't get to it. Now that it's going to be a driver escape, you'll be able to get to it from code. But the brightness, there is no concept of brightness control in the display driver, and I think it's a mistake. And you'll see everybody having separate DLLs that are backlight drivers. Regarding contrast control. Yes. A control panel that intercepts the contrast control. Well, that kind of leads to my point that before programmatically you could not control it. Only GPE could do it. And what I've seen people do is that the display driver then calls a contrast driver that is a standard accessible device in device.exe space, and so the display driver offloads the contrast control at least, so, and then that driver tends to call back in the display driver. Anyway, you do that so that you can have some third-party accessible or application accessible way to control contrast from one point. In 2.12, there's supposed to be a driver escape to do that. Is it in 2.1? It wasn't. It's in 2.10. So it's in there, but not documented. New revelation from the Windows CEDevCon. Isn't this great? So yeah, you could implement it now. It's a drive escape. Yes.
I want to reflect on, they were talking about software rotation.
Yes.
Your response was essentially do it in hardware, but that doesn't help a whole lot of systems who can't do it in hardware. What's it going to take, and this is more probably directed directly at Microsoft and OEMs, I mean, we got to get together on this problem. How do we get together and have maybe some optimized routines to help, the 80-20 rule, do the most we can with the littlest possible resources to get the acceleration, some acceleration with rotation. It's going to be a problem. It's going to get worse before it gets better.
Well, there's a major implementation issue before you even get to the fact that the driver doesn't support it, and that's that CE doesn't support dynamic resolution of the desktop changing, dynamic changing of the desktop. And so you have to do a warm boot because it calls get mode info only once. And because of that, even if you rotated, you'd have to reboot the device.
Well, I'm talking about, a lot of systems are coming where you have, natively, you have a landscape driver, but physically we're rotating the device, and therefore we rotate the frame buffer.
Yes.
So that, I understand what you're saying, but a lot of systems come up with with a rotated driver all the time. Okay, the native mode essentially is rotated. That's a real hit on performance as we start getting bigger sizes of screens and bigger pixel depths.
And a lot of the chip manufacturers are starting to support that.
Let me just say that it's a little bit of a trade-off, right? By us implementing it in the standard GPA libraries, that makes the rest of the system larger in all instances of the OS, or for us having that support. We have had relatively decent performance by doing the dirty rect driver, which gets you a rectangle that needs to be blitted, and you rotate that particular one. We provide a sample driver where we do that rotation in C, obviously for a particular application. Because that's going to be called anytime you have any dirtied area in the screen, you'd want to hand code that to be an optimized rotation in assembler for your platform, and you can really reduce the performance impact of that. But that gets you, we're always fighting we don't want to be too large. We want to do things the right way such that you can have the right level of performance without us trying to solve everybody's problems on all the variations of hardware. And we'll take 64 megabytes of hard drive space to be able to install this. So that's one of the decisions we've made, is that dirty rect it may not be the optimal solution of having every blit function and every GPE class item know how to deal with rotated screens, where you'd be writing to write a D word out, or to draw 4 pixels in a row, you'd have to write 4 separate D words on 4 different rows. That ends up being a fair amount of a performance hit just doing that operation. So it's actually, it's not much worse for you to have an optimized function that does the dirty rect operation. And it is a significant performance hit if you have to do software rotation. So if it's at all possible, you could also look at hardware that's the right layout.
What would you, if you were to recommend a general strategy, what would be the best way to optimize for rotation, software rotation?
Hardware.
Of course.
No, I'm sorry, but like SMOS has, the 1356 does hardware rotate. And the other solution is a lot of the accelerated chips that are out there, like the MediaQ chip, is supposed to be very fast, and they claim they can do software rotate because they just hook into their blit engine. If anybody's starting a system today, if they're designing a system from scratch today, and it's got any size screen at all, and any size color depth at all, and you're not using hardware acceleration, you're crazy. Okay, you should be trying to go for hardware acceleration because it is going to make such a difference. It just is an infinite difference. You can see the boxes on the show, well, you could have seen the boxes on the show floor, and you can tell the difference. You can just see it, just in their performance, and it's not because the CPU is faster.
Well, obviously, coming from the perspective that I have, we have multiple OEMs, and OEMs want 2 cents off of the BOM cost. So
And
Yeah,
it's
so
software.
I guess what I'm saying is I think it would be really great if we could get together and have
I'm
a
not sure
better
that, I
solution
mean,
here.
as we were saying, you know, if you're going to, I don't see any optimization doing it in GDI versus doing it in the driver. It's just that you write the code. And the advantage of you being able to write the code is that you can hardware it. You can take advantage of any kind of hardware acceleration, or, you know, quirks about your chip, or, you've got fancy chip assembler instructions that'll help you there. So, I mean, it's not going to be any faster.
Thank you.
Sorry. We didn't answer your question. We basically just told you tough. That was the answer in 10 minutes. Any other questions? Thanks much. Remember Sinbad. Oh, actually, ask the expert.